Lagadha. Over 3000 years ago, while much of the world struggled with basic timekeeping, the ancient Indian sage Lagadha was crafting astonishingly precise maps of the celestial movements. Living between 1200 and 1350 BCE, during the peak of the Vedic civilization, he pioneered what would evolve into one of humanity's most advanced astronomical works. His masterpiece, Vedanga Jyotisha, is the oldest known Indian astronomical text and the world's first detailed manual for practical astronomy, designed to guide Vedic priests in calculating exact timings for sacred rituals and sacrificial ceremonies. Think of the Vedanga Jyotisha as an ancient GPS system for time itself. Lagadha developed ingenious mathematical algorithms to track the movements of the sun and moon with remarkable accuracy. He calculated that a lunar year contained exactly 360 tithis or lunar days, while a solar year spanned 366 solar days, measurements that modern astronomers confirm were extraordinarily precise for their time. His work included sophisticated methods for predicting eclipses, calculating lunar months, and even accounting for the complex adjustments needed to synchronize lunar and solar calendars. What makes Lagadha's achievements even more remarkable is his identification of the winter solstice, occurring when the sun and moon were in conjunction at the beginning of the Shravasta constellation. Using this astronomical marker, modern scholars have been able to precisely date his observations to around 1373 BCE, a testament to the accuracy of his celestial calculations. Lagadha's systematic methods in astronomical observation and calculation laid the foundation for Indian astronomy and influenced later astronomers like Aryabhata and Brahmagupta. Aryabhata. Born in 476 CE in the thriving Gupta Empire, Aryabhata emerged from the scholarly city of Kusumapura, or the modern-day Patna, as one of history's most brilliant mathematical minds. At just 23 years old, this young astronomer would pen the Aryabhata, a masterwork that challenged everything people believed about the cosmos. When most believed the sky rotated around a stationary Earth, he boldly proclaimed that our planet spins on its own axis daily. In the Aryabhata, he wrote with poetic precision, and I quote, "In the same way that someone in a boat going forward sees an unmoving object going backward, so someone on the equator sees the unmoving stars going uniformly westward." This elegant analogy explained why stars appears to move across the night sky, not because they were actually moving, but because the earth itself was turning. His mathematical contributions were equally groundbreaking. Aryabhata calculated the value of pi as 3.1416, which is accurate to 4 decimal places, pretty impressive for that period of time. He constructed the first ever sine table by dividing a circle into 24 equal parts, creating tools that Indian astronomers would use for over a millennium. His yearly calculation of 365 days, 6 hours, 12 minutes and 30 seconds came remarkably close to the modern measurements. His model of the solar system used a geocentric approach, with the sun and moon moving on intricate paths he called epicycles that orbit the earth. But he also clarified in his works that planets and moon shine by reflecting sunlight and not emitting their own light, and gave a clear explanation for eclipses through the casting of shadows rather than old mystical ideas. Remarkably, his prediction of the duration of a lunar eclipse in 1765 was only off by 41 seconds, an accuracy discovered by later European astronomer Guillaume de Jontel. Another of his path-breaking work, the Arya Siddhanta, though lost today, is recorded through later scholars as an advanced treatise based on the ancient Surya Siddhanta, describing astronomical instruments like the Yashti Yantra, which is a cylindrical stick, shadow tools, and water clocks, and embracing the concept of midnight day reckoning. He even established an observatory at the Sun Temple in Tarigana, turning it into a hub for celestial study and observation. Aryabhata's legacy lives on. His pioneering approach inspired giants like Brahmagupta and Bhaskara I, and heavily influenced the creation of numerous Arabic astronomical tables or zais during the Islamic Golden Age. And later, his works gained recognition in the Western world through translations into Latin. Varahamihira. In the scholarly city of Ujjain during the 6th century CE lived Varahamihira, a remarkable thinker who studied the cosmos and weather with sharp insight. Born about a century after Aryabhata, Varahamihira blended insights from Indian, Greek, Persian, and Roman scholars, creating a vibrant fusion of astronomy and natural sciences. His Panchsiddhantika, written around 505 CE, unified 5 major astronomical treatises from, again, different nations, each packed with methods for tracking planetary motions, calculating solar and lunar cycles, predicting eclipses, setting calendars, determining solstices and equinoxes, measuring celestial distances and angles, and mapping the position of stars and planets with a blend of complex mathematical rules, tables, and observational techniques. He also introduced place value numbers, which simplified complex calculations and helped astronomers work with large numbers more precisely. Next came the Brihat Samhita, a wide-ranging treatise that detailed planetary conjunctions, weather phenomena, and the effect of eclipses and comets. It treated astrology as a study of natural patterns and covered topics like climate, seasons, planetary retrograde motions, conjunctions such as those between Jupiter and Saturn, and also the appearance of comets and meteors. So, in his works, every celestial event was analyzed for its timing and significance, making the Brihat Samhita a key reference for both astronomers and astrologers. Mathematical innovation also shines throughout his work. Building on Aryabhata's sign tables, Varahamihira introduced new interpolation methods that sharpened the precision of trigonometric calculations used to track the sun and moon's movements. He was the first Indian astronomer to quantify the Ayan or the slow shift of equinoxes at about 50.32 arcseconds per year, which eventually helped astronomers in improving calendars and the timing of religious ceremonies tied to the sun and the moon. It also allowed better prediction of seasons and alignment between observations and the shifting skies. While some traditionalists in Ujjain resisted his foreign influences, Varahamihira's blend of storytelling, practical guidance, and mathematical depth made a lasting impact. Future astronomers like Brahmagupta and even Lalla viewed him as a pivotal figure in India's cosmic journey. Brahmagupta, born in 598 CE in the vibrant town of Bhilmal, made lasting contributions to astronomy that shaped both Indian and global scientific traditions. His key works, the Brahmasvutta Siddhanta, written in 628 CE, and the Kandakya, written in 665 CE, offered sophisticated methods to understand and predict celestial movements with remarkable precision. One of his significant achievements was developing formulas to calculate planetary motions. He described how to determine their mean and true longitudes relative to the Earth, allowing astronomers to track planet movements more accurately. His precision extended to daily celestial events as well, proposing methods to find the exact rise and set times of the planets. Moreover, Brahmagupta calculated the length of the solar year as 365 days, 5 minutes and 19 seconds, a value impressively close to modern measurements. This accuracy helped refine agricultural calendars and the timing of festivals tied to the solar cycle. Brahmagupta's understanding of the natural world went beyond astronomy. He was one of the first astronomers from India who introduced the concept of gravity as an attractive force, described in Sanskrit as Gurutvakarshana. And he also wrote about the effect of gravitational pull in shaping planetary behavior. He was also clear about the Earth's shape, emphasizing its spherical nature and calculating its circumference at roughly 36,000 kilometers, a close approximation for his era. His understanding helped frame celestial calculations and spatial awareness of Earth in relation to the cosmos. Brahmagupta's blend of theory and practice shaped generations of astronomers. His work influenced Indian scholars like Bhaskara I and Bhaskara II, and it also reached Islamic figures such as Al-Khwarizmi and Al-Batani. Haridatta. By the late 7th century CE, Aryabhata's revolutionary ideas had shaped Indian astronomy, but they still remained confined to scholarly circles. Enter Haridatta, born around 683 CE, whose passion lay not in novelty but in accessibility. Working in the port city of Sopara, Haridatta recognized that complex astronomical calculations needed a wider audience beyond Ujjain's elite scholars. Haridatta's most significant contribution was the Parihatta system, a simplified version of Aryabhata's methods designed for practical use by astrologers, priests, and navigators. Rather than expecting every student to master dense Sanskrit sutras, he introduced streamlined computational procedures using a place value notation that even less trained practitioners could apply. One of Haridatta's ingenious ideas was the use of easily memorizable reference tables for mean motions. By providing pre-computed values for the daily movement of celestial bodies, he eliminated the need for continuous arcane calculations. The resulting ready reckoner transformed astrology and calendar making, thereby empowering temple astrologers to predict auspicious times for rituals and traders to chart seasonal winds and tides for safer voyages along India's vast coastline. Although Haridatta did not author a voluminous text like his predecessors, his system was widely adopted by astrologers from present-day Maharashtra to even Sri Lanka, some even crediting it to a mythical sage to give it ancient authority. This anonymity reflects Haridatta's humility. He sought not personal fame, but the sharing of knowledge. Lalla. Around 720 CE, a scholar named Lalla emerged in central India. Building on Haridatta's work that made Aryabhata's methods accessible, Lalla focused on refining techniques behind those methods while exploring new territory. Lalla's most celebrated work, the Sishadi Vriddhi Tantra, which roughly translates in English to Treatise to Expand Students' Intellect, offers a striking balance between the competing schools of Aryabhata and Brahmagupta by selectively blending their methods and correcting their concepts. Aryabhata championed Earth's rotation and advanced mathematical models, while Brahmagupta favored a stationary Earth with different computational rules. Instead of taking sides, Lalla synthesized their approaches. He adopted Aryabhata's mathematical precision and aspects of planetary calculations, while also integrating Brahmagupta's corrections, more practical computational schemes, and some of his philosophical stances. This allowed Lalla to build a more robust astronomy system. Lalla then also ventured into spherical astronomy and introduced original formula for the Earth's shadow cone during eclipses, and even sketched the earliest known perpetual motion concept in astronomical literature. Beyond theoretical advances, Lalla revolutionized practical astronomy by creating 12 precision instruments. His famous works describe them as sphere, ring, dial, bow, time-measuring water vessel, gnome, divider, scissor, circular seat with central stick, semicircle with stick, combination of sticks, basically forming the 12 instruments. These included the Gola Yantra or the armillary sphere for locating planetary positions, various protractors like the Bhangna and Chakra for angular measurements, the Ghati or water clock for timekeeping, and the Shanku or gnome for determining directions and measuring solar altitudes. Now, each instrument served specific observational needs, from the Kartari scissors like device for angle measurements to the Yashti Yantra measuring stick for calculating terrestrial heights and distances. Lalla sharpened the precision of planetary position and strengthened the math behind spherical astronomy, bridging theory and observation and making Indian astronomy both accessible and increasingly exact. Vijayanandi was born in 940 CE in the holy city of Benares or today's Varanasi. Vijayanandi's Karnatalaka, which loosely translates to Crown of Astronomical Computations, spanned 14 chapters and offered clear, methodical treatments of standard astronomical tasks, defining units of time, calculating where the sun and moon would be in the sky, determining day length, fixing the position of the 5 planets, and solving the classic 3 problems of diurnal rotation or the daily spinning motion of the Earth. His works would then help predict exactly when celestial objects would rise and set, determine the correct times for agricultural activities, and create accurate calendars that matched seasonal changes throughout the year. Unfortunately, the Sanskrit original has been lost, but its Arabic translation by Al-Biruni preserves Vijayanandi's specific algorithms and precise numeric tables connecting 2 major scientific cultures. He also refined sign tables and improved the previously used calculation methods to make his predictions more reliable. He was also one of the few astronomers who focused on testing his results against real sky sightings and actual observations, an approach which became more important in Indian astronomy over time. Sripati. In the early 11th century, the village of Rohini Khanda in Maharashtra was home to Sripati, born in 1019 AD into a family of scholars. Unlike many before him, who mainly studied planetary cycles, Sripati focused on the moon's irregular movements, specifically the small variations that make predicting its path tricky. Sripati is best known for his study of the moon's second inequality, a small wobble caused by sun's gravitational pull as the Earth and moon move together in space. In his work, Siddhantsikhara, written around 1039 CE, he carefully explained how to calculate this tiny variation by adjusting the moon's position using parts of the sun's motion and precise sign calculations. While modern scholars note some small errors in his formulas, Sripati's effort was India's first detailed attempt to measure this subtle effect, improving the accuracy of lunar predictions. Sripati's contributions to astronomy went far beyond his lunar work. His Dikoti Dakarna offered 20 verses focused on predicting solar and lunar eclipses, while Dhruvamansa detailed methods for calculating planetary positions, eclipses, and transits. He also worked on arithmetic in his incomplete treatise, the Ganita Tilak, which included rules for solving equations and managing positive and negative numbers, building on his predecessor's ideas but adding new examples. Sripati balanced mathematical rigor with practical needs. Temple priests used his eclipse tables to schedule festivals. Navigators relied on his astronomical algorithms to guide coastal voyages, and astrologers found his texts like the Jyotisha Ratnamal useful for casting horoscopes with refined data. Sripati even offered one of the earliest Marathi texts, making complex astronomy accessible to local scholars in their vernacular. Eventually, his legacy inspired later astronomers like Bhaskara II to improve lunar predictions even further, showing that understanding the sky depends on mastering its smallest movements. Mahendra Suri. In the mid-14th century, under the reign of Firoz Shah Tughlaq in Delhi, a Jain scholar named Mahendra Suri emerged as a pivotal figure in Indian astronomy. Born around 1340 CE, Mahendra Suri immersed himself in the rich traditions of both Sanskrit scholarship and Islamic astronomical learning, which had entered India through the Sultanate's cultural exchanges. Mahendra Suri's crowning achievement, the Yantra Raja, written in 1370 CE, marks the first Sanskrit treatise dedicated entirely to the astrolabe, a device essential for precise celestial observations and timekeeping. Rather than presenting astrology as a mystical art, he treated the astrolabe as the king of instruments, offering a detailed user's manual that explained how to construct, calibrate, and even employ both the Nadan or Soumya and the Sadan or Yamya types of the instrument. Despite the Sanskrit presentation of Yantra Raja, Mahendra Suri's treatise remained firmly rooted in Ptolemaic and Islamic traditions. Soon after its completion, his student Mahendra Suri composed a commentary that enriched the text with ready reference tables, listing latitudes for over 70 cities and key stars, simplifying calculations for temple astrologers, travelers, and court scholars alike. However, Yantra Raja's reception was mixed. Traditional Sanskrit orthodoxy greeted it with caution, wary of its foreign mathematical underpinnings. Yet, among practicing astronomers, both in Indian courts and the wider Islamic world, his manual became a vital bridge between diverse scientific cultures, influencing observation practices well into the Mughal era. This also ensured that India's astronomical heritage continues to remain both innovative and inclusive, welcoming knowledge from every corner of the medieval world. If you would like to explore more stories from ancient India stargazers, let me know or leave a comment below. And please like, share and subscribe for more such legendary stories from our past.